Hello and welcome to another week of ECE 108. So this week we're going to start off by finishing up our discussion of combinatorics, and then we're going to change topics ever so slightly and start talking about discrete probability. So let's jump right in. So in the last lecture I ended with talking about binomial theorem, and I promised that I'd give an application of binomial theorem to counting, so let's do this. Given a finite set S with n members, the number of subsets of S, denoted by this quantity here, is 2 to the n. So how would I go about computing the number of subsets of a set S? Well, for the proof, the number of subsets of size m, where m is between 0 and n, what would that be? Well, if S has n elements, and I want to pick m distinct elements from S, how many ways are there to do that? Well, just by definition, that's going to be this binomial coefficient here. So this quantity here tells me the number of subsets of size m, so how could I compute the number of total subsets of S? Well, I can simply split up the subsets of S based off their size. So thus the total number of subsets of S is simply going to be the sum of the number of subsets of m elements, for m is 0, 1, all the way up to n. Okay, so from here I get that the cardinality of this set will simply be the sum of all of these binomial coefficients. So how do I add up all these binomial coefficients? Well, I used binomial theorem. So from here I know that this is simply 2 to the n, and again, this last equality comes from our work in lecture 21, so if you want a refresher, just go examine it. Okay, so this is one application of the binomial theorem to counting. So in our last few lectures, we formally tackled how to handle the unordered without replacement, the ordered with replacement, and the ordered without replacement. So the last kind of class of combinatorics problems that we have left to handle that we haven't examined yet is our unordered with replacement. So let's look at these problems. Recall example 5 from lecture 18. So here I was starting a new D&D campaign with 4 people, and we had 4 classes that each of the people could choose from, and I wanted to know how many parties could be formed. So we solved this problem previously by using a brute force type method. So explicitly, previously we painstakingly went through 5 disjoint cases, taking 4 slides to solve this problem. Is there a better way of solving this problem? Well, yes, like many counting problems, if I do something clever, I can usually save myself a significant amount of work. So instead of examining the problem in its current form, I'm going to view it in a slightly different formulation, and ultimately this new formulation will allow me to use combinations to solve this problem very, very quickly. So what is this new formulation? Well, instead of thinking of this problem written out like this, I'm going to think of the problem like this. So here I have all of my classes at the bottom, so each one of these is written here. Here I wrote lines to separate the classes, and here I put little dots in some of these bins. So explicitly, what are these dots representing? Well, these dots represent the players playing a given class. So within this structure that I've written here, this represents 1 player playing a cleric, 2 players playing a monk, and 1 player playing a wizard. Now, you might ask, how does this help me? I just wrote the problem in a slightly different way. Well, if you notice here, I have 11 sticks, so 12 minus 1 of these sticks, and I have 4 balls. Now, if I were to take one of these balls and move it to another slot, say take this element here from monk and change it over to fighter, for instance, that's changing my party composition. So my party composition is uniquely determined by the ordering of these lines and these circles. So to be explicit in this formulation, the problem becomes finding the number of reorderings of the lines and the circles. So let's continue this discussion on another slide. So again, here's the problem that I started out with, and here's my reformalized version of the problem. So how many ways can I put the dots between the lines? So here, notice that the order of the dots within the lines doesn't matter. It doesn't matter if I have line, this dot, that dot, then this line, or line, bottom dot, top dot, and this line. That's the same party. But the order of the lines with respect to the dots does matter. So if I have this dot here for cleric and say move it over here to make it a dot for druid, those are two different parties. So what I'm going to do is I'm going to rewrite this above problem here in this form here. So in this case, I have the two lines for barbarian and bard, followed by a dot for cleric, followed by these lines for druid and fighter, followed by the two dots for monk, etc. Now, this thing here is just a string of characters. In particular, it's a string of 11 of these lines and 4 of these dots. So now I can ask a combinatorics question. How many ways can I pick a location for the 4 dots in the above string? And notice that this question here is equivalent to this top question here. So if I can compute the number of ways that I can pick a location for the 4 dots in this string here, then I know the answer to the number of parties that can be formed with 4 players and 12 classes. So how would I compute the number of ways that I can pick the locations of the 4 dots? Well, there's 15 characters here, and I want to choose where 4 dots go. So this will simply be 15 choose 4, and I can evaluate this out. This is simply this expression here, or 1,365, and this is the value that I found previously. So whenever I have a unordered with replacement type problem, you should identify what the bins are. So in this case, barbarian, bard, etc. But whatever the bins are, and you should identify the quote balls or the dots or the stars that you're putting in the bins and reformulate the problem as one of these, find the orderings of this particular string, and then use a combination to solve the problem. So you might ask, can we drive a general principle where I don't have to go through that process? Well, the answer is yes. And to kind of start motivating that, well, first notice that the above, 15 choose 4, is simply 12, so the number of classes, minus 1, this is the number of these bars, plus 4, choose 4, right? So does this work in general, where I just say bins minus 1, plus balls, choose balls? Does that work? Well, yes. So let's give a definition. The k out of n multi-choose is going to be represented by these double bars here, n choose k double bars. So we're going to define this by n plus k minus 1 choose k. So this is exactly what I did over here in the case where n is 12 and k is 4. So that's where the motivation for this definition is coming from. And here, multi-choose is the tool needed to quickly solve unordered with replacement problems. So now, just one comment here. Previously, when I dealt with combinations, I really only cared about the case where n was bigger than k. That is not the case for multi-choose. So if n is less than k, then this term here in the top of the binomial coefficient is still larger than this term in the bottom. So I still have a non-trivial combination, and in terms of my combinatorics problem, that would be representing a problem where I have fewer bins than I have balls. So if I go back to the D&D example, say if I wanted to play with 13 players and still only 12 classes, that's a well-defined combinatorics problem, and thus this multi-choose would still be non-trivial and well-defined. So one final other note, this is often called the stars and bars method because oftentimes people use stars here instead of dots, and they still use the bars. So if you ever want to use this multi-choose method, you can just say, applying the stars and bars method, That's a way that you can write up your homework problems. Now let's look at a couple of examples using this method. So I'm making a smoothie and I have an unlimited number of chunks of frozen strawberries, blueberries, banana slices, and spinach leaves. A natural question I might want to ask is how many smoothies can I make if I pick 12 items to include? So given this unlimited stockpile of things, what are the number of different smoothies that can be made? So here you can notice that this is a unordered without replacement problem. In my smoothie, I don't care if I put the strawberry in first, then the blueberry. Once I blend it, it's going to get mixed together anyways. And it's with replacement because I can pick multiple strawberries, blueberries, banana slices, or spinach leaves. So to solve this problem, I'm going to appeal to multi-choose. So here, how many classes of items are there? Well, there's 4, right? Strawberries, blueberries, banana slices, spinach leaves. And I need to pick 12 of these. Thus, if I were to do the stars and bars method directly, there would be 4 minus 1 is equal to 3 bars. So to be explicit, this is what my bins would look like. So I have exactly 3 of these bars here. And I need to pick 12 items, so I have 12, quote, balls in this case. So thus, I'm going to have 4 multi-choose 12 options. So notice here that 4 is less than 12, but this is still well defined. So if I wanted to explicitly compute this, there would be 12 plus 4 minus 1, choose 12, or 455 possible smoothies. So this really beats doing the method that I introduced in lecture 18, where I broke the problem down into a bunch of subproblems, found the number of ways to solve each of the subproblems, and added them up. It's significantly faster, so you should definitely make sure you understand these examples. It will make your life significantly easier. Further on that note, I could pick numbers such that you can't physically go through and compute this number of possible outcomes by hand. So for instance, if I picked this to be 10 to the 500 and I had 800 possible bins, that's too many cases for you to physically write down. So make sure you understand this method. Okay, so that said, let's look at another example. 51 passengers get onto an airport shuttle. This shuttle goes to 6 different hotels. Each passenger gets off at their hotel, and everyone gets off at exactly one of the 6 stops. A natural question that I could ask would be, how many ways can the passengers get off the shuttle? The first thing we need to do is identify what type of problem this is. Well, here I'm treating each one of these 6 different hotels as a distinct bin, and I have 51 passengers, but I really am not drawing a distinction between the passengers, so I could treat the passengers like balls in this case. So here in this example, the hotels represent the bins, and the passengers are the balls. So this question is really asking, how many ways can I rearrange strings consisting of 51 passengers and these 6 different hotels, or 5 bars, if you will? Well, that's simply a multi-choose problem. So there's going to be 6 multi-choose 51. So evaluating this out, this would be 51 plus 6 minus 1, choose 51, which if I compute that is 3.8 million ways that the passengers can get off the shuttle. So now there is another useful way to restructure this problem, and this new way that I'm going to introduce right now is very useful to solve a lot of the problems that I will be giving you. So again, another useful way to solve this problem, if xi is equal to 0, 1, 2, is the number of passengers who get off at hotel I, then I can restructure this problem as wanting to find the number of solutions to this linear equation here. So these types of problems come up all over the place in probability and in counting, and you'll see a couple of examples in your homework assignment. So let's examine this problem in general to talk about how I would try to solve problems like this by giving another example. What are the number of distinct solutions to this linear equation here, where each xi is a non-negative integer and k is greater than or equal to 0? So here I have this extra restriction on k simply so that I can have at least one solution. Well, how would I possibly go about trying to tackle this problem? Well, if I look at the previous example, the hotel problem can be formulated in 2 ways. One way was finding the number of solutions to this equation here, and the other way was simply doing this multi-choose. So this kind of implies that the answer to the question on the next slide will simply be take the number of things that I'm adding together, put that at the top of a multi-choose, and take the value over here and put that at the bottom of the multi-choose. That should be my answer. And it turns out that that actually is the case, but just to give you another example of going through the process of doing the stars and bars, let's drive it from scratch. Okay, So there are n minus 1 lines. So in this case, the lines are simply going to be these plus signs that are splitting things up here. Now, in this case, what are my stars or my dots going to be? Well, here I want to assign each one of these x sub i's a number, and I want those numbers to add up to 12. So between these plus signs, I'm going to assign a number of dots based on the value of each one of these x sub i's. So if x sub I was 7, I put 7 dots. If x sub I was 10 million, I put 10 million dots, etc. So again, just putting that in words on the slide. For xi is equal to L, I'll place L balls to represent x sub I. Now again, what's the total number of balls? Well, if I add up x1, x2, all the way up to xn, I end up with k. Therefore, there's going to be k balls for this case. So let's graphically look at this just to give you a better idea of what this is saying. What if I was examining the case where k is equal to 20 and n was equal to 3? Well, this would be one possible solution. So here within my stars and bars framework, this would have 2 bars sitting here for each one of the plus signs, and then I would have 7 dots for this first one, 3 dots for this next one, and 10 dots for the last one. So this is what my problem would look like within the stars and bars framework. And the question that I would have to solve is, given these 2 bars here, and given 20 balls that I could put in either of these 3 places, how many ways can I rearrange that string? Well, the answer to that would simply be I have my multi-choose. Now I have 3 bins, so I'd have a 3 on the top, and I want to multi-choose where 20 of those would go. So in this case, this would simply be 3 plus 20 minus 1, choose 20. And of course, I could simplify that out to get a value. Okay, so let's go back to the general framework now that we've kind of seen how this translation from the equation to the bars works and kind of solved it for one particular case. So here, the solution would thus be n multi-choose k, again, n because I have n elements here, and k because that's the number of balls that I'll be putting in. And again, this is simply n plus k minus 1, choose k solutions. Now, the most important thing to really get out of these examples is the process, not the quick and easy throw in the final answer. So sometimes it's very useful to just jump straight in and say, yeah, that's multi-choose, there, I'm done. But in other times, I could have a question that's not quite in one of these exact formats that I presented. And for those problems, you need to use a modified version of this multi-choose to solve the problem. So let's look at an example where I want to find the number of distinct solutions to some equation where I'm not exactly in this form. Say if I want to know what the number of distinct solutions to this inequality is, where x1 is equal to 1, 2, da-da-da, and x2 and x3 are non-negative numbers. So you can notice pretty quickly that we can't directly apply our previous results for 2 reasons. 1, x1 cannot be 0, and 2, I no longer have an equality, I have an inequality. So I have to address both of these things in order to solve this question. So how am I going to do that? Well, let's pick one of these things to address first, and since I mentioned this x1 can't be 0 first, let's deal with that. So to address the first problem, I'm going to introduce a new variable that is in z0 plus, and how am I going to do this? Well, I'm going to let y1 be equal to x1 minus 1. So let's check to make sure that works. If I take a number that's 1, 2, etc., and I subtract 1 from it, that indeed will be an element of z0 plus. So using this formulation, I can rechange this inequality by solving this for x1 and substituting it in. So doing that gives me that this x1 plus x2 plus x3 is less than or equal to 5 simply becomes y1 plus 1 plus x2 plus x3 is less than or equal to 5. And this inequality can be rearranged by simply getting rid of this plus 1 by subtracting it. So from here, I can rearrange this to simply be an inequality of this form. So here I've now satisfied the issue where x1 was not an element of z0 plus, since y1, x2, and x3 are all elements of z0 plus. Now, this trick of modifying one of the variables to make the problem easier should always be in the back of your mind when working on these problems. So now I've simplified this problem here to simply finding the distinct solutions to this, and now I somehow have to deal with the less than or equal to. Well, how can I do this? There's two kind of classic ways that you can go about doing this. One of them involves case analysis and does not scale well, and the other one does not involve case analysis and does scale well. So for the case analysis, what you would simply do is you would examine this inequality here, and then you could notice that the largest value that I need for one of these variables is simply the value of 4, right? So then you could say let y1 be 4, go through the different cases, and then you could say now let y1 be 3, go through the different cases, let it be 2, go through the cases, let it be 1, go through the cases. And in each one of these cases, you need to consider the possible rearrangements where instead of it y1 being 4, what if it's x2? So you'd have to keep track of all of those little details. It's not too difficult to do, but it's not the most optimal method. So let's look at a better way. So instead of doing that, I'm going to add a new variable in a very special way. I'm going to add a new variable called a slack variable, and this is going to be some non-negative integer, such that z is equal to 4, the number over here, minus the sum on this side. So how does this help me? So first, is z really in z0 plus? Well, I know this sum is going to be less than or equal to 4, so the possible values that can come out of this total difference here is 0, 1, 2, 3, or 4. So indeed, z is an element of z0 plus. So now how does this new variable help me? Well, if z is equal to this expression here, I can add this term here to both sides, and I can restructure this as y1 plus x2 plus x3 plus z is equal to 4, where y1, y2, y3, and z are all in z0 plus. I know how to solve this problem. That would simply be multi-choose 4, because I have 4 elements here, over 4 because I have a 4 on this side. But why does this equation have the same number of solutions as this inequality? Well, for any given y1, x2, and x3 such that their sum is less than or equal to 4, I could then pick z to be explicitly this thing here, and that would give me a solution to this. So for every solution to this equation here, there is a solution to this equation here. Now, for any given solution to this equation here, I could throw away z, and it would be true that y1 plus x2 plus x3 is going to be less than or equal to 4, because if I get rid of the z here, I get this inequality. Thus, there's a bijection between the solutions here and the solutions here, so the cardinality is the same. That's the basic idea for why I can do this. But in general, anytime you have a problem like this inequality, you can always add this type of a slack variable to consider this equation instead. Okay, so from here, again, the number of these solutions is simply this term here, which is simply equal to this, which is 7 choose 4, or 35. So there are 35 integer solutions to this under these restrictions here. So this process of turning a problem like this into a problem like this that I can handle is very important, and you definitely should make sure you understand this example. Now let's look at another example purely in Paint, and then I'll add it as a formal slide after I'm done. Example, what are the number of ways that you can roll 3d6 to get a sum of 12? So here, this problem is similar to these type of problems, but I have an extra restriction, and you're actually going to have a homework problem similar to this, so that's why I'm adding this now. Okay, so first I need to convert this problem into a problem of one of these forms. So how do I do that? Well, I'm rolling 3d6, so I can let x1, x2, and x3 be each one of these rolls, and I want x1 plus x2 plus x3 to be equal to 12. Okay, what are the restrictions on x1 through x3? Well, these are coming from dice rolls, right? So each one of these xi is going to be an element of the set 1, 2, all the way up to 6. So now there's a problem with this. In the previous examples, my domain for each one of the xi's started at 0 and it went off to infinity. Here I have the restriction where I have to stop at 6. Thus, if I directly tried to use the multi-choose to this, I would overcount the number of solutions because I would include things where one of the dice rolls was a 12 and the other two was a 0, and that is not possible. So how do I overcome this problem? Well, one way would be to use material that I haven't introduced yet, but I will introduce in lecture 23, called the principle of inclusion-exclusion. So what I could do is I could first find the number of solutions to this with no restriction. And then from here, I could turn around and subtract from that the number of solutions that violate my restriction. And in general, there are times when you explicitly have to really use this method. And even though we're trying to avoid using this method, you'll ultimately see that we need to use it for this problem as well. But we can do a transformation that reduces the number of bad solutions we have to subtract off. So let's let y sub I, for I is equal to 1, 2, 3, be equal to 6. So I'm picking the end of this range here, minus x sub I. So let's notice some properties about this. So first, this implies that x sub I is simply going to be equal to 6 minus y sub I. Okay, so from here, what else can we notice? Well, if I'm going to do this type of transformation, I want to plug this into here and see what the new equation is. And I also want to use the fact that x sub I is in this domain to find my new domain for y sub I. So let's do both of those processes real quick. So plugging this in, I'm going to get a 6 minus y1 plus 6 minus y2 plus 6 minus y3. So if I kind of simplify that a bit, I have 6 plus 6 plus 6, so that's 18. So here I'll have an 18, and I'm going to have minus, well, once I do this transformation, I'll simply have my y1 plus y2 plus y3. And all of that will be equal to 12. Okay, so now simplifying this, I can rewrite this equation as follows. Okay, so I've changed this constant here from a 12 to a 6 by doing this transformation here. So does that solve my problem? Well, maybe, maybe not. I don't know what the domain of my y sub I elements are. So let's figure out what the domain is. Well, if x sub I is equal to 6 minus y sub I, and x sub I is between 1 and 6, how can I find what my y sub I are? Well, let's look at an inequality real quick. So over here, I could say 1 is less than or equal to my x sub I, which is less than or equal to 6. So this inequality is the same thing as 1 is less than or equal to my 6 minus y sub I, and that will be less than or equal to 6. So here I can solve this inequality using basic methods that you've learned in high school. And solving this would give me a 5 on this side, so 1 minus 6 gives me a negative 5, divide by a negative. Greater than or equal to, again, negative y, when I divide by that I flip the sign, y sub I, and 6 minus 6, that would be 0, and that gives me this bound here. So sadly, this transformation didn't fix all of the issues, right? 5 is less than 6, so I could have the case where one of these things is 6 and the other two are 0, and that would be a violation of this assumption here. So I would do some double counting if I still use the multi-choose, but it's significantly better than all of the double counting possibilities I had before. So let's run with it. Okay, so how would I do this? Well, from here, the number of solutions to this thing without restrictions, so explicitly, this quantity here, what would that be? Well, I know I have 3 elements and I want to multi-choose 6. So that would simply be multi-choose 3 of 6. So chasing that out, this would be 3 plus 6 minus 1, choose 6. Or, so 3 plus 6 minus 1, what's that? Well, that's 8. So this is 8, choose 6. So that's simply going to be 8 times 7. That's dealing with my 8 factorial over 6 factorial. And all of this would be still divided by a 2 factorial, or just 2. So 4 times 7, that's simply going to be a 28. So just a reminder here, you can do these by hand for small problems. Okay, so this is the numbers without restriction. I need to now subtract off the elements here that I counted that were bad. So for this case, the restriction that I want to add is that y sub I has to be less than or equal to 5. And if I look at my equation over here, I had the possibility of y sub I being equal to 6. So how many ways can y1, y2, or y3 be equal to 6? Well, that's simply going to be 3. So here, the solution to this, putting it together, would be 28 minus 3, which is simply equal to 25. So in this case, there are 25 number of ways that I can roll 3d6 to get a sum of 12. And to find it, I took my non-standard problem here. I turned it to another non-standard problem that had a easier restriction on it in terms of being able to count the solutions I overcounted. I found the number of solutions to this equation where I had no restriction other than the y sub i's were non-negative. So that's the straightforward problem that I've done on the slides and did in a couple of examples. And from there, I subtracted the number of solutions with this extra restriction that I need to impose for this upward bound. So if I ever ask you to do a dice solving problem, say one of the problems that is on your next assignment, this is the type of thing you might want to do if you find yourself in the situation where the number on this side is bigger than the number here. And by bigger, I mean bigger by a significant margin. Also, do note that this particular transform here where I used 6 is not the only transform that you can use. So you do need creativity there, just keep that in mind. Okay, going back to the lecture slides, we now can talk about my TLDR recap. So methods that we've covered so far. Previously, we've talked about all of these. I can now add one new method to the list, and that's going to be picking k items from a list of indistinct items with replacements. That will be in choose k. So here, my list of distinct items is my bins, and my k items are the items that I'm picking from. Okay, so let's look at our assigned reading. I want you to read pages 75 through 77. So in there, there's a couple good examples to look at. So just look at those as extra examples to see. And then from there, we have a meme. So this course is going to be super unintuitive, sure. Yeah, so generally students find this multi-choose to be a bit unintuitive when you first see it. But once you start thinking of it in terms of the stars and bars and rearranging those strings, that should help to clarify it a bit. So if you do have questions and do get stuck on it, ask in Piazza or office hours. It is something that you might find confusing at first glance.